Right, now my talk was going to be all about reconciling multiplicative physiological noise and additive psychophysical noise. But I haven't made as much progress as I was anticipating with this, because I got sidetracked by some other stuff, which turned out to be quite interesting. So I'm going to talk about the other stuff first, and then at the end I'll get on to the relationship between physiological and psychophysical noise. Now, imagine we're doing two alternative false choice contrast discrimination studies where the observer has to discriminate between a pedestal contrast, CP, and a target contrast, CP plus delta C. It's been known for decades that if you plot the threshold value of delta C against the pedestal, you get a dipper shape. These data are from Napier and Sainsbury, who published one of the first dipper functions, although not the very first. And we can model this using a transducer followed by additive noise. A commonly used transducer has this form, and the expansive part of the transducer at low contrasts causes performance to improve with increasing pedestal at low contrasts, and the compressive part of the transducer at high contrasts causes performance to get worse with increasing pedestal at high contrasts. Now, I actually fitted this transducer to Napier and Sainsbury's data, and you get a very nice fit. And to do that modelling, I assumed that the noise was Gaussian, like most people do. But as Daniel mentioned right at the beginning, Peter Neri has recently argued that the internal noise actually has a Laplace distribution, which is has considerably higher kurtosis than a Gaussian. Now, Peter reached this conclusion using some reverse correlation methods and some very clever analysis that I don't fully understand. But it got me wondering about whether the same conclusions might apply to noise-free stimuli. Of course, we can't use Peter's methods to look at this, because the methods involve adding considerable amounts of noise to the stimuli, so we need to find some other way of looking at it. And we can find out something about the shape of the internal noise distribution from the shape of the psychometric function. A commonly used mathematical form for the psychometric function is the Weibull function. P is the proportion correct, and alpha and beta are parameters. The beta parameter affects the shape of the function. And Dennis Pelly famously showed that for the case of Gaussian noise, a power function transducer with exponent B and zero pedestal, Weibull beta is approximately equal to 1.3 times B. Now, Josh Solomon and I have a paper in Press in which we derive an expression that gives Weibull beta for any noise distribution, any transducer, and any pedestal. We find that Weibull beta can be partitioned into two factors, which we call beta noise and beta transducer. Beta noise is the beta of the Weibull function that fits best to the cumulative distribution function of the noise. And it takes a value of about 1.3 for Gaussian noise. Beta transducer depends on the transducer and pedestal, and it's given by this expression here. Now, for a power function transducer with exponent B and zero pedestal, this expression for beta transducer reduces simply to B. So using these two equations to substitute for beta noise and beta transducer in the equation at the top, we obtain Pelly's expression, beta equals 1.3 times B, for Gaussian noise, a power function transducer, and zero pedestal. So Pelly's expression is a specific case of a much more general expression that we've derived. Now, for the next few slides, all the text within this blue box is going to stay the same. For a power function transducer with exponent B and non-zero pedestal, we get a more complicated expression for beta transducer. W is the Weber fraction. And for a leg Foley transducer, it gets even worse. It's not a pretty expression, but it does accurately estimate vital beta for this model. But it turns out that for the purposes of the argument I'm going to make now, we don't need to worry about specific transducers, because we've proved that for an expansive transducer, beta transducer is always greater than 1. For a linear transducer, beta transducer equals 1. And for a compressive transducer, beta transducer is always less than 1. And taking this last case, for a superthreshold contrast discrimination, for which the transducer is in the compressive region, we can combine these two relations to conclude that vital beta must be less than beta noise. And remember, beta noise is the beta of the vital function that fits best to the noise CDF. And it takes a value of about 1.3 for Gaussian noise. What about Peter's Laplacian noise distribution? Well, it turns out that the CDF of Laplacian noise is actually a vital function, with beta equal to 1. So, for the Laplacian noise CDF, the best fitting vital function fits exactly with beta noise equal to 1. And so, combining these two relations, we conclude that for superthreshold contrast discrimination and Laplacian noise, we predict that vital beta should be less than 1. But the trouble is, measurements of vital beta for contrast discrimination very rarely fall below 1. Here's a histogram of beta fitted to superthreshold contrast discrimination data from a range of studies from different labs. And there are a few beta values less than 1, but most of them are greater than 1, inconsistent with Laplacian noise. The median value is 1.43, and this value actually implies a noise distribution with lower kurtosis than Gaussian, which is the opposite of Peter's conclusion. Now, I'm not saying that Peter's made a mistake, but clearly something doesn't quite add up, and it would be interesting to try to get to the bottom of this. And one possible solution is that both Peter's analysis and mine assume that the signal goes through a deterministic transform followed by additive noise, and that model may be wrong, as Peter suggested just now. Now, Stan Klein indicated in his talk that there's been quite a big research effort into trying to find out whether the internal noise is additive or multiplicative. Additive noise is signal independent, multiplicative noise is signal dependent. And not that long ago, Johnston and Means argued that on this issue, the jury's still out. Physiological noise is usually found to be multiplicative. And on this basis, some people argue that the noise in psychophysical models should also be multiplicative. On the other hand, other people whose psychophysical models have additive noise have cited papers that suggest that maybe physiological noise is additive after all. But the point I want to make in this final part of the talk is that additive noise at the psychophysical level is not inconsistent with multiplicative noise at the physiological level. And to demonstrate this, let's take a really simple neural population decoding model where we have a set of spiking neurons with identically shaped contrast response functions which are uniformly spaced along the log contrast axis, starting at some minimum level. And let's also assume the actual number of spikes on each stimulus presentation is sampled from a possible process which produces multiplicative noise. And we'll assume that the brain takes the spike counts from each neuron and uses a Bayesian decoder to infer the log contrast. If we repeatedly give the model the same stimulus, we get a distribution of decoded log contrasts. And it can be shown for this particular model, the standard deviation of the decoded log contrast is independent of the stimulus. It's easy to see why this is the case, So if we move our stimulus from here to here, if the contrast response functions are all identical and they're uniformly distributed along the stimulus axis, then if we shift the stimulus, we're still faced with the same kind of decoding situation, but it's just shifted up the contrast axis. And so we get a distribution of decoded contrasts with the same width. So the noise in the decoded log contrast is signal independent. And this means for high contrasts, these high contrasts within this range of the neuron's contrast response functions, the model is equivalent to a log transducer followed by additive noise. So we have additive noise at the psychophysical level and multiplicative noise at the physiological level. So how does this model do on standard contrast discrimination experiments? Well, for low pedestals, performance is poor because the neurons are not sensitive to these low contrasts. When the pedestal reaches contrasts that the neurons are sensitive to, performance starts to improve. And for high pedestals, the constant noise on the log contrast axis gives rise to Weber's law when threshold is expressed in linear units. And if you look at this Dipper function, you may get a feeling of familiarity because I actually fitted the parameters of this model to Napiers and Sansbury's data that I showed you right at the beginning. So in conclusion then, psychophysical models in which a deterministic transform of the stimulus is followed by additive noise are not inconsistent with multiplicative physiological noise. But this kind of psychophysical model is probably wrong because it leads to conflicting conclusions about the kurtosis of the internal noise distribution. Using this kind of additive noise model, Peter's analysis of detection of bars embedded in noise implies that internal noise has higher kurtosis than a Gaussian, whereas my analysis of variable beta for superthreshold contrast discrimination implies that the internal noise has a lower kurtosis than a Gaussian. And I think the possible resolution of this apparent inconsistency is to abandon the assumption that a deterministic transform is followed by late additive noise. And I think maybe the model that Peter mentioned just now with gain control may be one solution to this. Okay, thank you.
A couple of minutes of questions. If anyone Stan looks like he's making a beeline for the microphone.
One thing that's puzzled me forever, ever since Frank Quick invented the Weibull function, is why do people use the Weibull function? Why are you focused on the Weibull? Why not Gaussian?
I think I'm interested in Weibull fits because it's so the Weibull function is so commonly used. You know, people started using it because of probability summation models and stuff. But even though the field has moved on and nobody believes that stuff anymore, people still fit Weibull functions to the data. But lots of different models will deliver different mathematical forms for the psychometric function. But people still do Weibull fits, partly because the Weibull function is built into Quest. And so it's useful to understand what happens when you fit a Weibull function to a psychometric function that's not a Weibull.
One wonderful question is, how can we change the world to abandon the Weibull function?
Maybe we don't have to.
Does anybody else have questions? Because I come to the you're asking us questions. But if not, no, quickly. Keith, also in your observation is based on the assumption that the beta transducer is you are in the compressive region, which is unchecked. In the sense that, for example, if you do have, as you said, a gain control model, that you may not be in that region. You may be brought back to another operating range within the transducer.
Quite possibly, but if we have a gain control model, then the equations that I've derived don't apply anyway.
Yeah.
So it's just really a test of that simple model in which a deterministic transform is followed by additive noise.
And obviously, without making any assumption about where you are in the transducer, I imagine you cannot, because at that point, beta transducer can take any value, greater or smaller than 1, and then it's not possible to reach a conclusion. I mean, what I'm saying is that you have to make some assumption there, right?
You do, but if the pedestal is reasonably large, you can be pretty sure that you're in that compressive region.
For the linear model, yeah.
Yeah.